Good morning. This is Sharon Starr, IPC's Director of Market Research, and welcome to this week's Wisdom Wednesday webinar, which is actually on a Tuesday this time. It is covering some highlights of IPC's PCB technology trends study from 2016, just recently published. And we have with us today Mike Carano, to give us an overview of the findings. But first, just to let you know what's in the study, it's a survey-based study covering the major trends and technology issues, primarily in PCB fabrication, also some in assembly, and covering all sorts of aspects of board design, performance, capabilities, materials, structures, new technologies, etc. And the survey participants provided their current measurements and what they project their measurements for the same things will be 5 years out in 2021, affecting the future of PCB needs and capabilities for the industry. We collected data from 18 companies, OEMs, EMS companies, and PCB companies all around the world. Demographically, 61% of the companies participating are in North America, which is a reflection of IPC's membership base. But we did collect data from every region of the world. And in all the different vertical market applications, 5 of which are actually segmented in the report, separate data for automotive, defense, and aerospace, high-end systems, industrial, and medical. So now I'd like to turn it over to our speaker. We're happy to have with us today Michael Carano, who's the Vice President of Technology and Business Development for RBP Chemical Technology in Milwaukee. And he's going to share with us his great insights into some of the data from this report. Welcome, Mike.
Thank you, Sharon. Yes, and as you can see here, the investment priorities of the PCB fabricators are heavily skewed towards the high-density interconnect technology. This has been a loud and clear trend globally, but also in North America. We are seeing the increased densification of circuitry, and that's being driven largely by advances in packaging technology, chip technology, system in a package, etc. So this has been very, very critical for fabricators going forward, and that's driving their investments not just in equipment for high-density interconnect, but also in laser direct imaging, embedded passes, and as you'll see later, printed electronics, and other techniques for this marketplace. Next slide. Now, as I said, the trend is miniaturization, and we have seen, by and large, with the electronics industry continue to show, optimism in higher density and in making the proper investments. We're seeing a need to reduce board thicknesses, and this is one of the beauties of high-density interconnect. If you can adopt that technology and adopt it successfully, you will see the potential, to reduce layer counts, also the form factor and the thickness itself of the circuit board, reducing weight, but you can also increase functionality, and that is a very critical aspect of this technology, and we're going to talk more about that as we move through this presentation. As I said before, high-density interconnect, 28% of the respondents said, they were doing this in 2016, but in 2021, the respondents was going to jump to 41%. So you can see there is definitely, this is definitely on the radar screen, and they're definitely hearing this from their potential customers and the OEMs in the marketplace. With this goes line widths and spaces. When you have increased densification, you're going to see smaller holes, higher aspect ratios potentially. At the same time, you have to add more wire density if you're going to reduce layer counts and truly make HDI an effective enabling technology for your business. And you can see how the feature widths and spacings are decreasing, and that of course is going to be driving more and more investment into laser direct imaging and surface preparation processes and technology. Now, how do you achieve these finer line widths and spaces in addition to improvements in imaging? Well, for the longest time, our industry, as you can see smack dab in the middle there, subtractive technology, basically laying down the image, exposing, developing, etching, and stripping, and etching away, 1 ounce of copper, 1.4 mils to define the pattern. But as we get into these finer lines and spaces and these requirements, it's going to take adjustments in the way we process printed circuit boards, and we see a lot of that now moving towards additive processing, which is basically building up your circuitry on unclad copper laminate, or you move into semi-additive processing, which is basically starting either with a very thin copper foil, or you can start with a 1 ounce half ounce copper foil and etch it down part way, or you can build up your circuitry on like a build-up film, such as the Automotive film, and these give you very, very fine line opportunities for higher density and densification of circuitry. Now, with that goes reduced pitch, surface mount packages, but most importantly, as we see here in the area array packages, BGA, micro BGA, as we get more and more functionality on the chip, stacked chips, known good die, we're pushing the pitch into a tighter and tighter tolerance. And we expect these to go down also, companies like in the internet infrastructure space, and also in the in computer storage and cloud computing. They're going to be seeing more and more of the I/O pitch shrink as we try to put more and more I/Os in a smaller area. Along with that, of course, is forming the micro vias. You can't be in the HDI business without understanding how to form blind vias and micro vias. Basically, micro vias we typically define as anything as 6 mil in diameter or less, but we think the majority of the market is starting to center around 3 to 3.5 mils in diameter, and some even going lower, as you can see here. Now the question is, we'll talk a little bit how we're going to get there, but you can see this is definitely not only putting more vias, in a feature or a surface area, that is going to also drive finer lines and spaces. So this, you can see how this all comes together from an investment standpoint: imaging, via formation, and as you'll see later, investing in surface preparation, interlayer treatment processes, and of course metallization or plating. Now, we talk about high-end systems, and Sharon showed that in one of the early slides about where in the supply chain are the various companies consider themselves. If you look at some of their roadmaps that INM has put out, and in the past IPC, typically high-end systems, which actually accounts for quite a large amount of the industry supply chain in terms of dollars spent. This is typically high-end systems are storage systems, enterprise communication, also data centers and internet infrastructure. Those are the ones we consider high-end systems, base stations, etc. So we picked this particular group to highlight here because of the significant high aspect ratio that we're seeing in terms of the plated through holes. As you can see already, that number is a 16:1 aspect ratio in 2016 for these high-end applications, moving to almost 22:1 by 2021. And on the right side of that slide, you can also see where they expect the aspect ratios for micro vias to be. And again, this is an average, but when they say a 1.0 for aspect ratio for blind vias, you're talking, you'd say a 3 mil blind via, 3 mils deep. But we also expect that some companies will be doing 2.5 mil blind vias and maybe potentially 3.5 mils deep, which will knock that aspect ratio up to about 1.3. And you'll also see some plated through holes, as you see on the left here, well above 21.8 to 1. Again, this is going to put additional pressure on not just via formation and high quality drilling, but also going to put some pressure on us from a plating standpoint, how we metallize these holes and these vias. Now, with blind vias comes the need for do we have to fill these vias? And again, it's going to depend a lot on OEM preference. But there are techniques that are, up till now, at least for this current level of technology, and at our board level, we do have a definite good cadre of techniques used to fill these vias, whether they be via filling paste, which is a ceramic filled epoxy that can be screened into vias and cured, and then later planarized and plated. We also see a big growth in area of copper via filling, or what we call super fill. And again, this is using plating techniques or potentially even copper sintering paste to plate the vias completely full. And of course, along with that goes the need for proper plating processes, equipment, agitation frames, and controls. But those are all right now well established for the current technology level. As we move forward, in the next 3 to 5 years, and those aspect ratios become more challenging, it stands to reason that they'll need some improvements in plating processes. Will it go to periodic pulse reverse plating? That's also a good possibility, and we'll have to wait and see how this technology continues to go, to higher aspect ratios, and what response the supply base can make to handle these issues. Next slide, please. Now, there's also a lot of talk in the industry about, okay, when you're building these high density circuits, there's obviously micro vias. You have multiple laminations, potentially 3, 4, 5 layers on each side of a core with blind vias in them, or micro vias. Well, there's also a lot of talk about the reliability of whether the vias should be staggered, in other words, slightly offset, or could they be stacked, neatly, perfectly registered, on each other. Well, there's a number of studies going on right now in publications that questions the reliability of stacked vias as compared to having staggered vias. So I encourage you to look at and talk to the some of the OEMs that are participating in this, some of the consortia like HD Pug that have also working on this very same problem. So there is concerns about stacked versus staggered, and this is a good discussion for designers to have with the fabricators and also the OEMs, because this will be and has been showing as an issue moving forward from a long-term reliability standpoint, thermal cycles and cycles to failures. Next, please.
There it goes. Okay.
Here we go. Now that brings us to another important aspect of our study here, and that's materials. Next slide, please. From a material standpoint, we see that, as you can see, multifunctional epoxy systems, this typical FR4 tetrabromo bisphenol A and its iterations continue to dominate the use of rigid materials. And there's still quite a subset of other materials, such as polyimides and glass reinforced, the PPOs and the PPEs, but the multifunctional epoxies continue to be the standard resin system used in the industry today. Next slide. Now, along with that, the question is, there's the need for materials to be lead-free assembly compatible, and so material suppliers have been working diligently to improve not just the electrical performance of laminate materials that are low loss and exhibit higher dimensional stability, but they're also developing materials that can also withstand the higher temperatures of lead-free assembly. And that brings us to that slide that shows here that as opposed to what conventional FR4 laminates were dicey cured or dicyandiamide, which is a cross-linking agent, the industry is moving to enhance the thermal properties, if you will, and ability to withstand higher temperatures of assembly by going to phenolic Novolac cured epoxies. Why is that important? Well, obviously you want the improvement, of course, in lead-free assembly to be able to stand up to that and the laminate to not decompose. But as a ramification to fabricators, these materials drill differently, so your drill bits might wear out faster. You might have to make some adjustments in how you de-smear and how you plate. So that's something that I'm sure many of you are aware of, but it's worth taking a look at if you've gone to a phenolic cured and your customers are all lead-free assembly. Next slide, please. Now, metal core boards. There's quite a subset of fabricators here in North America that we work with, all of us work with every day, that are building circuit boards with copper, Invar copper, aluminum core, even aluminum backed boards for a number of techniques, for a number of end markets and end uses. A lot of what we see here is not just the ability for these materials built with the metal core to have some increased dimensional stability, but they're also acting to help dissipate heat, particularly for the LED industry, light emitting diodes. We know that they generate quite a bit of heat, and having metal core fabricated boards, and for lighting in general, automotive lighting is becoming a big part of this industry. So acquiring some expertise in using metal core fabrication in your circuit technology is critical if you're trying to get into a niche market here in North America. Next slide, please. So again, we've got that particular group there representing the market, about 9%. Now, where are they shaping out at is typically in the metal core. We see a lot in industrial applications. That's going to be the main driver, for this for metal core.
I'm sorry, I'm having some difficulty advancing the slides. Let me try this again. There it is.
There it is. Okay. Again, that's just showing you that the main driver for this is the industrial market, and this is what we're seeing is LED lighting, airplane, airway lighting, new improved lighting in people's homes. Again, these materials, being that application, LED is going to generate a lot of heat. You see again an increase in use of metal core. Next slide. Now that comes here with the next important aspect of our discussion on these organic substrates, these high performance laminates for the reasons we talked about: low moisture absorption, higher performance in terms of temperature, assembly, etc. There's also the need to have even a broader application with that's being driven by bandwidth miniaturization and increased data transfer rates. This is the telecom industry, internet infrastructure, cloud computing, and this is driving the need for low loss and ultra low loss materials, laminate materials used in circuit board fabrication. So this is very, very critical. But in addition to that, we're going to talk about some of the other issues later with surface preparation and surface treatment. But for now, look at the move or the growth in these low-loss materials. Obviously, the standard FR4 materials are still going to dominate. That's quite clear. But in the internet infrastructure space, microwave circuitry, you're seeing this increase in the need for low-loss and very low-loss materials to minimize signal loss and enhance the signal integrity in your electronic systems performance. Next slide, please. And this also shows that even besides the telecom internet infrastructure group, automotive is showing a large increased need for ultra low loss materials. Why is that? We're talking about everything from the Internet of Things to vehicle communication to crash avoidance. So the automotive industry has become a large consumer, not just of the circuit boards in general, but of these low loss and ultra low loss materials that will drive the DF well below 0.004. So stay tuned for that as this technology comes forward to the forefront, and more fabricators will need to adapt to this material, both in lamination and also surface preparation and adhesion promotion. Interestingly, and I remember first seeing somebody demonstrate stretchable electronic materials 15 years ago, and I didn't know if it was going to go anywhere, and obviously for a lot of years it didn't. But there seems to be some indication now that the participants in this study, which didn't indicate much in 2016 in terms of stretchable materials, they are definitely looking to invest in it and bring on some expertise by 2021. So this will be very interesting. There'll be some specific niche applications for this, and we'll just have to go from there. Next slide, please. Yes, halogen-free laminates. You can't have a discussion on technology trends and technology in general without an understanding of what's going on besides the low-loss materials, what's going on the environmental side. Roche compliance, various countries pushing for completely halogen-free, regardless of whether it's a bound halogen or not, in the materials that are used in devices, whether they be electronics or the clothes you wear or what have you. This is obviously, I expected a bigger jump in this, but regardless, 50% of the participants expect 50% of the laminate area that they will be producing or making circuit boards with by 2021 will be completely halogen free. Right now it's 46%. A lot of that is driven, I think, on the consumer side in Asia right now, and mobile phones and like Apple and companies like that are driving to the halogen free markets, and of course in Europe. But we'll see more of that here, and again, that will put more pressure on fabricators to understand how to drill and how to process these materials, how to desmear these materials in order to get the best possible performance and reliability out of their circuit boards. Another area that we've seen a lot of interest in is printed electronics. And interestingly, even today, 9.3% of the companies surveyed did say they incorporate some, type of printed electronics, whether it be for quick turn production, prototyping, or what have you. But we expect that number is going to change according to this survey, and by 2021, 21.3% say they plan to incorporate some printed electronics technology in their business. Now, next slide, please. And typically, what I've seen over the years, not just RFID devices, but even 4 and 6 layer circuit boards pressed together, made by printed electronics. Solar cells, batteries have been done that way. But as you can see here, this is the industry is estimating what's typically going to happen here going forward, and where the possibilities are for printed electronics. The equipment is fairly well developed, but I think they need some more improvement in the large format printing, the ability to deliver conductive inks to a substrate, and also how you're going to process those substrates later on. Potentially flexible circuits might be, at least in my opinion, might be a good opportunity for printed electronic applications. Now, going forward, what about 3D printing? This has been one of the very interesting technologies coming out recently about how to mold devices, complete devices in fewer steps, with potential to print the circuit and also the device maybe, and have a functional electronic device. There are some 3D devices produced today on 3D printers, and the technology is being advanced very rapidly in terms of not just resins being used, but also in the equipment to do the 3D printing. But again, as you can see here, while there's 16% of the respondents did say they're using 3D printing somewhere in their business today, that number goes to almost 25% by 2021. There's a number of technical challenges also cited, by the respondents. We've talked about this. Again, HDI is very critical going forward. Everything from via formation. How are we going to do that? Are we going to use special mechanical drilling? Are we going to use CO2, UV, YAG lasers? Again, the good news is the opportunity for high-density interconnect, smaller diameter vias, and even small diameter through holes has been, been completely enabled by improvements in drill technology, drill machine, drill speed, positioning, registration, etc., and also specially designed drill tools. That's very, very critical. That allows us to go to higher aspect ratios. Of course, we're requiring thinner dielectrics so we can meet the HDI mantra of increased functionality in a smaller space. That will require, obviously, improvements in lamination, registration, etc. Heat management, how would we do that? Maybe heat sinks, thermal vias, etc. The loss requirements have been well established as we move forward here. We do want not just lower DF, signal loss, but we want improved adhesion, reliability, and performance of profile-free and ultra-low profile copper. That's going to be part and parcel to this as well as we move forward. And then any improvements we can make in copper plating consistency. We're getting uniform distribution of the plated copper across the surface of a panel and through the hole. And along with that goes reliability. Reliability requirements, you got to put more reliability into the via, whether it's a through hole, whether it's a micro via. And how we do that with improved plating technologies, more ductile copper, materials that can withstand significant thermal stress in the Z-axis. All of these will be critical going forward.
Mike, thank you so much for all of your insights on just a small sampling of the data from the PCB technology trends study. And since there's very little time for questions, what we'd like to do is offer you the opportunity to send us emails with your questions. Contact us by email or phone. If you have questions about the research, how it was done, the survey, our methodologies, I'm the person to contact, and here is my email address and phone number. And if you have any questions about the data and the technology issues underlying the data, Mike is happy to try and address your technical questions. Here is his contact information. And this will be posted, this entire presentation will be posted on the IPC members only site, so you can refer to it later. And I want to thank you again, Mike, for this excellent presentation. And thank you all for attending this Wisdom Wednesday webinar. I hope we'll see you again next month. And so thank you and goodbye.